Hello everybody, and thank you for joining me for the last lesson on Chapter 1 for Year 13 Stats and Mechanics, Regression, Correlation and Hypothesis Testing. So we've calculated regression using the calculator, we've worked out that correlation lies between values of -1 and 1. Now what we're going to do is return to the idea from Year 12 of a hypothesis test, but this time we're going to be testing how certain we can be if two sets of data have correlation or not. So we can apply hypothesis tests to these to test if they are related linearly or if maybe it's just a coincidence they seem to be. So we're going to have a look at that in a moment, but before we do, I've got two warm-up questions for you, and because we're doing hypothesis testing here, I've returned to Year 12 type hypothesis testing with these warm-ups. So if you've got your handouts, try these now. If not, pause the video now, make a jot of the question, drop the question down and try it on your own. And when you're ready to see the solution, press play and we'll have a look together to see what the answers are. So without waiting anymore, let's have a look now at question number 1. So question 1, a potter believes that 20% of pots break whilst being fired in a kiln. Pots are fired in batches of 25. So we're asked to let X denote the number of broken pots in a batch. A batch is selected at random. Use a 10% significance level, find the critical region for a two-tailed test of this potter's belief. We need to state the probability in each tail of the critical region. So what I'd suggest we do first of all is to sketch out this on a little grid. So if I let this be the variable x, and of course x can take the values from 0 to 25 because this is the batch size. So 0 is where none break, 25 is where they all break. So X is going to follow a binomial distribution, 25 pots, and the probability of any one pot breaking is 20%, which is 0.2. So typically, 20% of these 25 will break. 20% of 25 is 5, so you'd expect about 5 typically to break, so the distribution should be like this. 5's the most common, and then hopefully you'd imagine that all 25 break would be pretty rare indeed, or so you'd hope. So what we need here is a two-tailed test. We're testing at the 10% significance level, so what we need to do is to split this in half, so we need less than 5% in each tail. So this region here, that must be less than 5%. And this tail over here, wherever it may lie, that also needs to be less than 5%. So we're getting as close to 5% as we can without actually being over 5%. So the way we do this is we get our calculators for ClassWiz like so, and we go into the binomial mode. So we press menu, we press option 7 for distribution. Now we want binomial CD, so we press down to get to binomial CD, and we press 2 for variable. So n is our number of pots, which is 25. Probability of any one pot breaking, or proportion of broken pots, we assume to be 0.2. And we're just going to try different values for x. We want x to be as close to 0.05, or I should say to generate a probability as close to 0.05 as possible without going over. We can't have this tail greater than 0.05 because then it'd be over 5%. So let's try 1. That's about 2.7%, so that's fair enough. Could we go up to 2 and still be under 5%? Well, no we can't. That's about 10%. So the closest we can get to 5% without going over is 1. So therefore, that down at this end, the critical region would be x being less than or equal to 1. So that's the first bit of the critical region. So I'll write that down. Critical region is x less than or equal to 1, but also we're going to have a critical region here. So at the other end, that means as a curve increases in terms of proportion of a curve, for example, here's about 50% of a curve, 60, 70, 80, 90, we want to find the cutoff for where 5% of this curve is. We want to get as close to 0.95 without going over. So you'd be surprised how quickly you can do this using trial and error, really. So for example, I could try 8, 0.95, that's gone over. Is that the first one to exceed 0.95 though? Well, let's just try. Maybe 7 would have been enough. 7 or less wouldn't have been critical. That's less than 0.95. The first value that exceeds 0.95, in other words, the first value that takes us within this 5% tail, as we can see here, is this one. But this is working out the probability of the observed number of broken pots being 8 or less, which is 0.953. So I'm going to make a note of this down here, because this can be confusing if we're not careful. So that tells us a probability of having up to 8 pots broken, that equals 0.953. Therefore, that tells us that the chance of having 9 or more broken will be 1 minus that probability, 1 minus 0.953. In fact, maybe I can go a bit more accurate with this. It's not 0.953, a bit more accurate, I can say 0.9532. And that gives 0.0468 to 3 significant figures. And so the critical region at the higher end is 9 or more. That's the first value that falls within the critical region. So remember, when we're at the higher end, we need to do 1 minus the other probability. So for critical region down here, that's x less than 1 or equal to 1. And also, it's this and the union. You could say and, or you could go union joined with this one here. And this one here is 9 or greater. So now we can start looking at part B. But before we do, we need to, as the question says, state the probability in each tail. So for this one here, it is less than 5%. So this probability here, we worked out from before, if you remember, was 0.0274. This one over here is 0.0468. So we've got as close to 5% as we can, but we can't exceed it. So for part B, what it's saying here is a potter aims to reduce the proportion of pots which break in the kiln, as you would want to do, by increasing the size of the batch fired. He now fires pots in batches of 50, and he then chooses a batch at random and discovered there are 6 pots which broke whilst being fired in the kiln. Test at the 5% level of significance whether or not there is evidence that increasing the number of pots in a batch has reduced the percentages of pots that break whilst being fired in the kiln. State your hypothesis clearly. Well, the null hypothesis goes that just assume nothing's changed. So the null hypothesis would be that H0, the proportion of broken pots, is still 0.2. The alternate hypothesis here is that the proportion of broken pots has been reduced. So H1, the alternative hypothesis, is a probability is less than 0.2. So based off the null hypothesis, which we assume to be true by default, if he's firing 50, it'll be binomially distributed with 50 fired, probability of the broken pot being 0.2. So again, if we picture this distribution here, down there's non-broken, up here is 50. 10% of 50 would be 10. You don't need to sketch on 10, but just give you an idea of what you're expecting to be normal. So 10's the most common number broken, trailing off, becoming less and less likely the more and more break, unless you're very, very unlucky indeed. So 10 is the norm. So what he's discovered here is that 6 pots have broken. So we need to work out if 6 is in the critical region or not. Or we can work out the probability of having 6 or fewer that break and compare that to this 5% level of significance. And in fact, that's what I'm going to do. So what was the probability of this happening? What was the probability of him seeing that only 6 or fewer pots broke? Well, now we just use a calculator again. So this time we change n to 50. The proportion by h0 we still assume to be 0.2, and this time we calculate based on the observed value being 6. Press equals and equals again. We see here this time that we get a value of 0.103. So that's about a 10% chance. So fairly unlikely, only a 10% chance that only 6 or fewer would break, but it's not so unlikely, it's not 5% unlikely, is it? So although it's unlikely, it's not so unlikely that it would force him to reject H0. So ultimately that's greater than the 5% level of significance. Because it's greater than that percentage of significance, it's not that noteworthy. So because this value is greater, we end up accepting H0. So we conclude by making reference to the original question, therefore accept H0. In other words, insufficient evidence to suggest that P has decreased. And that's question 1 done. We'll now have a look at question 2, which is another question on statistical hypothesis testing. So for question 2, we've got about houses in Radville. So the proportion of houses in Radville which are unable to receive digital radio is 25%. And in a survey of a random sample of 30 houses taken from Radville, the number X of houses which are unable to receive digital radio is recorded. So find the probability that the number of houses, X, without digital radio is in between 5 but no more than 11. So what's the probability of the number of houses from 30 numbered either 5, 6, 7, 8, 9 or 10? So let's just think about this in terms of different inequalities rather than just one. So we want the number of observed houses without digital radio to be less than 11. So less than 11, just to make a little note down here, is anywhere from 0, 1, 2, 3, 4, all the way up to 10, but not including 11. So this here, we want to work out the probability of up to 10 houses, but no more. Okay, so that's going to be all of these values here. But we want the smallest number of observed houses without radio to be 5. We don't want less than 5. So we don't want these here, 0, 1, 2, 3 or 4. So we need to take away from this the probability of observing 4 or fewer houses that don't have radio. So we need to just scrub off 0 to 4. So we just use our calculators again in the similar way to before. So here we go to menu, option 7, binomial CD, because we're talking about inequalities here, and go for variable. We've got 30 houses. The probability according to this is 0.25 of a house not receiving digital radio. And first of all, we want to work out the probability of 10 or fewer houses not having radio. So we type in n as 10. So what's the chance of 10 out of 30 having no radio signal? Press equals, and we get here 0.89427-ish. So this is going to be 0.89427 or so. We can obviously round this off later on. We're going to take away from that the probability of 4 or fewer. So for the next part, go back to the calculator, press AC, and type in 4 out of 30. So 4 out of 30, the chance of 4 or fewer having no signal, press equals is 0.09787. 0.09787. And then from these two values, we just take away one from the other, and we get our final solution. So menu 1, 0.89427, subtract from that 0.09787, and then we can round it to a suitable degree of accuracy. If we do that, oh, we don't need to round in fact at all, so 0.7964 will suffice. So about an 80% chance that between 5 and 11 houses won't have any radio signal. And that's part A done, so we can now turn our attention to part B of the question. So here, we've got this radio company, and it claims, this company, that a new transmitter, if it was set up in Radville, would reduce the proportion of houses which are unable to receive digital radio. After the new transmitter has been set up, a random sample of 15 houses is taken, of which only one house this time is unable to receive digital radio. Test at the 10% level of significance the company's claim. State your hypotheses clearly. So this time, the null hypothesis yet again will always be that there's no change. So H0 for proportion of houses without signal is 0.25. Whereas this company is claiming to reduce that proportion so that fewer houses will be without radio, so they're claiming the proportion of houses without signal is going to reduce to something below 25%. So I'd always suggest to just sketch out the curve here. We're sampling 15 houses this time. So from 15 houses, it could be that none of them have signal, which should be a bit wild, or it could be that none of them are lacking signal. So it could be that they all lack signal, or none of them lack a signal. As it turns out, only one house lacks a signal. So one is down here somewhere. If it was 25%, we'd expect typically a quarter of these 15 houses, so about 4, to not have any signal. So we'd expect the curve to be peaking around 4, and obviously very unlikely either side of that. So one house is down at the lower tail, so we're looking to see if 1 is going to be critical. So what's the probability of observing only 1 or 0 houses without any signal using H0? So by H0, we can say that it's going to be binomially distributed, 15 houses, and assuming H0 to be true, which we always do in the first instance, the proportion of houses without signal is 0.25. And based off that, the probability of observing one house or fewer without signal can be worked out using our trusty calculator. So if we press AC, menu, option 7, binomial CD, then option 2. So you want to work out the probability of just one house out of a total of 15, one or fewer houses, I should say, out of 15, having no signal, where the chance of no signal is 0.25. Now this comes out at about 8%, as you can see, 0.0802-ish, 0.0802. So 10% level of significance would be about here. And 8% is obviously smaller than 10%, so 8% is within the critical region. It's in this smaller area down here because 8 is smaller than 10%. So this here, we need to say, is smaller than the 10% significance level, smaller than 0.1. Because of that, this value here is critical. So therefore, because it's in the critical region is 1, we're going to reject H0 and make reference to the context of a question. There is therefore evidence to suggest that the proportion of houses without signal has decreased. Proportion of houses without signal has decreased. So always, if possible, return and make a clarifying statement based on the original context of a question. And that's all there is to it. So now we're going to have a look at hypothesis testing to check if there is correlation or not. This is going to be the main part of the lesson today. So, introducing hypothesis testing for zero correlation. So, how do we do it? Why do we do it? What does it mean? So we can use a hypothesis test to determine whether the product moment correlation coefficient, denoted by R, for a particular sample indicates that there is likely to be a linear relationship within the population. So typically R denotes the PMCC for a sample from the population, and the Greek letter rho, which looks almost like a P, this is called rho, that denotes the PMCC for the entire population. So if you want to test whether or not the population PMCC rho is greater than 0 or less than 0, we can use what's called a one-tailed test, because you're looking at one end either on the small side, less than 0, or on the large side, positive, where it's greater than 0. So we can do this in one of two ways. The first way is to say the null hypothesis is there's no correlation, rho equals 0, and the alternative hypothesis is that rho is greater than 0. And that would be a setup for a test to test if there's either no correlation or positive, whereas a second line would be the two hypotheses to test whether or not there's negative correlation. On the other hand, if you wanted to test whether the population PMCC rho is just simply not equal to 0, that would be a two-tailed test. If someone's just saying it's not equal to 0, they could mean one of two things. If it's not equal to 0, you could have either a positive correlation or a negative. That's why I need to test at two tails, one at the negative end and a tail for the positive end. So to do that, your null hypothesis would simply be that rho is 0, and the alternative hypothesis wouldn't be that rho is necessarily positive or negative, but that simply rho is not equal to 0. So this symbol here is a giveaway that we're talking about a two-tailed test. The critical region of the sample PMCC, R, for your hypothesis test can be determined by using the table of critical values on page 191 of your lovely Pearson Edexcel Year 2 Stats and Mechanics book, which you should all have. However, a version of this table will also be provided for you in the Mathematical Formulae and Statistical Tables booklet in your exam. So you'll always have access to that in your exam. Do not ever be thinking you need to memorize these tables. You don't need to be doing that. They'll always be given to you. The critical region for each hypothesis test depends on two things. It depends on the significance level of the test and also the sample size that R is calculated from. Here's a sample of one of the tables, which has been highlighted to show an example of how it might be used. So here you've got your product moment coefficient and level of significances, 10%, 5%, 2.5%, 1% and 0.5%, and running down, these rows are the sample sizes. So how does this work? Well, this is a sample like I've said, and so I've highlighted here 5% significance level and a sample size of 8. So if you wanted to do a test at the 5% level of significance with a sample size of 8, you'd read down at 5% and across at 8 and see where they cross, and where they cross, which I've highlighted in red, is the critical value of R. So the critical value of R for 5% significance, sample size 8, is 0.6215. So that means that the region of acceptance, where you'd accept H0, is where the magnitude of R is in between minus 0.6215 and 0.6215. So the magnitude of R needs to be less than that region of significance. The critical region, where you'd reject H0, is where R would be smaller than minus 0.6215. That would be evidence to suggest that the correlation is negative. And also the critical region would be where R is greater than 0.6215. That would suggest correlation on the positive end. That would suggest that rho is greater than 0, positive correlation. Typically though, for one-tailed tests, the sign of R we're testing for is implied. You can work it out from the wording and context of the question. I'll show you what I mean by that in just a moment. So next, to summarize, you can put it into a table like so. You don't have to, but I'm just going to show you a table to illustrate the point, and I'll refer back to this table in the two worked examples. So H0 and H1 and the general procedure. So case 1 could be that your null hypothesis is there's 0 correlation. The alternative hypothesis is that there's positive correlation. That would be a one-tailed test at the positive end. Let's call the significance level S. So the procedure for this would be you'd find the critical value of R subscript critical, for that significance level S, and you'd accept H0 if the observed value of R is less than the critical value of R. And you'd reject H0 if the observed value of R is more than the critical value. So this isn't to scale. So imagine rho for the population correlation. No correlation, perfect negative, perfect positive. If you're testing for positive correlation, a critical value will be somewhere here. If your observed value is somewhere here, you'd reject H0 and say there's evidence of correlation. If your observed value is down here, if it's lower than the critical value, you would say to accept H0 and that there is probably 0 correlation. If, however, you want to test for a negative correlation, where rho is less than 0, similar idea but at the other end. So you'd find your critical value for that particular significance level S. You'd only accept H0 if your observed value of R was greater than negative value of the critical value of R. The table will only ever give positive values. So if you're testing for negative correlation, you take the negative value and multiply by -1. There's symmetry around the 0. So if you're testing for negative correlation, same idea, just multiply the critical value you find in the tables by -1. So if it's less than the critical value, what you observe, somewhere down here, that's in the critical region, you'd reject H0. If what you observe isn't quite as negative as minus the critical value from the table, somewhere here, you'd still accept H0. So these are the two types of one-tailed test. If it's a two-tailed test, like so, where your alternative hypothesis is just that rho is not equal to 0, it's two-tailed, you're going to have 2 bits for your critical region at either end, like so. So what you do here, this is important, you halve the significance level and apply half the significance in each tail. So for example, if your significance level was 10%, you'd go 5% here and 5% there. You'd still find the critical value for that significance level which you've just halved, S over 2, and you'd accept H0 if your observed value is greater than the negative version of critical value, but less than the positive version of critical value. So you accept if it's somewhere between these 2 bits. You'd only reject H0 if your observed value is smaller than minus what the critical value is read as, so somewhere down here, or you'd reject it if your observed value for R is higher than the positive critical value, which would be somewhere here. This will make more sense when we apply it with some worked examples. So I've also included in your notes a table of critical values attached at the end of the suggested exercises from the book. Let's have a look at a worked example then. just to make it clear. So we've got here a scientist taking 30 observations of the masses of two reactants in an experiment. She calculates for PMCC to be minus 0.45. This scientist believes there's no correlation between the masses of the two reactants. Test at the 10% level of significance the scientist's claim, stating your hypotheses clearly. Well, first of all, let's get this table up so we can work out how to use it. So here's a section of the table. Now, we're told here that she's using 30 observations. So 30 observations means we need to go to the sample size of 30 and highlight that, because that's what we want to be looking at here. The next thing is, it's tempting to think it's 10% significance, so read off at 10. However, just be really careful, think about what she's saying. So H0 is almost always that there's going to be no correlation. So H0 is that rho equals 0. That's what she believes. So always go with H0 being that there's no correlation, and then go with the alternative hypothesis being that there is. Now this scientist is just saying that there is no correlation, and there's no saying if we want to test for positive or negative. So if you're just saying that there's no correlation, the alternative is that there is correlation. There could be correlation which is positive or negative. So all we need to say is, if it is correlation, then the correlation is not 0. And this, therefore, is going to be a two-tailed test. So what we need to do here is we take this 10% level of significance, we're going to divide that by 2 and test 5% in each tail. So because we're trying out 5%, 5 in the lower tail, 5 in the positive tail, we're going to be reading off at 0.05. So we're going to look down here, and therefore what we're interested in, our critical value for R is 0.3061. So at this stage now, it might well be worth getting that diagram up, similar to what we had in that table, just to think about what's going on. Okay, so the critical value we've got is 0.3061. So I can actually swap out this and include what it is. So the critical value is 0.3061. Therefore, minus R critical is going to be minus 0.3061. So now we compare that versus what she's actually observed. So she's observed R being minus 0.45. Obviously this isn't drawn to scale, so don't pull me up on this. I mean, obviously minus 0.3 would be about here, it's not to scale. But if this is minus 0.3, and that's minus 1, then minus 0.45 would be to the left. It'd be more negative than minus 0.3061. So what she's observed, minus 0.45, is in the critical region at the 10% level of significance, in other words 5% at each tail. So what we can say here is that minus 0.5 is more negative than the size of the critical value. It's more negative than minus 0.3061, which we find from the table. Because of that, it's in the critical region, which means we therefore reject H0. So we then conclude by returning to the context of the question. So we just need to say something along these lines. We're going to reject H0, and we can say something like, there is evidence to suggest that there is negative correlation Don't even need to say negative really, you just need to disprove what she's saying, negate what she's saying, but there's negative correlation between the masses of the two reactions. Bit of writing, but it's not going to hurt you too much. And that's what we need to say in our conclusion to pick up our marks, which ultimately is probably all you're interested in. So that's worked example 1. Let's have a look at another worked example, which is, as you can probably guess, a fairly similar idea. This one was two-tailed. How would it look if it were one-tailed? Well, here we've got a table from the large data set, and it shows below the daily maximum gust, X knots, here on the top row, and the daily maximum relative humidity, Y% in Leeming for a sample of 8 days in May 2015. So already, before reading the question proper, we can probably anticipate what we need to do. We can see here there's a sample of 8 days, so let's just get the table up and ready again. It says here, like I mentioned, that it was 8 days, and so we need to be looking at the sample level of 8. So our critical value of R is going to be one of these ones here. Anyhow, first of all, find the product moment correlation coefficient for these data. So this here is just a calculator job. So what we're going to do, get the calculator, we're going to press menu, we're going to scroll to statistics. We want a linear relationship so we can work out what the linear PMCC would be. So press 2. Then we just type in our values for X and Y. So 31 first. Then we're going to type in 28. Next is 38, 37, 18, 17, 21, 29. Then scroll back up and type in the corresponding values for Y. So when X is 31, Y is 99, then 94, then we've got 87, got 80 twice, then 89, 84, and finally we have 86. So we then press equals one final time, then we press OPTN to get options. So OPTN, we want regression calculation, so press option 4, and we see here that R for this sample is to 4 significant figures 0.1149. No working needs to be shown, it's a waste of your time ultimately. Just write down what your calculator says. The examiner is fully prepared for you just using your calculator for these. The main thing is you need to know how to use your calculator. Some people don't. Don't be one of those folks. So that one, we've got for A, for R equals 0.1149. Simples. Now for part B, test at the 10% level of significance whether there is evidence of a positive correlation between daily maximum gust and daily maximum relative humidity. So here it's saying clearly positive correlation. So it's a one-tailed test at the positive end. So hypotheses would be as follows. So H0, no correlation, rho is 0, and H1 is that there is a positive correlation, in other words, rho is greater than 0. So our level of significance is 10%. We don't need to divide that by 2 because it's a one-tailed test. So we just look at where 10% falls, that's 0.10. So looking here, where they cross over is what we're interested in. So our critical value for R is 0.5067. Again, if you want to use a graphic, this might help you. So you can probably remember from the previous subchapter that R of 0.1149 is pretty damn weak. So 0.1149, our observed value is about here. So that's R observed. whereas a critical value of R, which we've just looked at from the table, is 0.5067. So as you can see, R observed, which is 0.1149, is nowhere near the critical region. It's not anywhere near being positive enough. So for B, we just need to say this essentially. So for B, all we need to say is that 0.1149 is less positive than the critical value of 0.5067. Therefore, we're not in the critical region, in fact, nowhere near. So then all we need to do is just make a closing statement to conclude. So we just say, therefore, we're going to accept H0 in other words, there's not enough evidence. I apologise again for my writing, I wish it was neater. But there's not enough evidence to suggest positive correlation between gust and I've run out of space like a silly person, so forgive me for this. A bit amateurish, but you know, it's not the worst thing I've ever done. So accept H0, not enough evidence to suggest positive correlation between gust and the other variable, which was daily maximum relative humidity. So again, there's often a tiny bit of writing to do at the end, but it's not the worst thing that could happen. Just make sure you make a conclusion, going back to the context of the question, to make sure you do enough to pick up that final crucial mark. So I'm just underlining the final answer there. So if you write something like this, or a version of it, you'll be good as gold. So now it's over for you to try some of these yourselves, and I'm hoping with a bit of practice you'll see actually these don't bite, and they're relatively speaking straightforward. So if you turn to page 10 through to 12, exercise 1C in the Stats and Mechanics book, try question 1 through to question 4, then question 6, and to finish off I'm suggesting question 9 and 10. And you know the drill by now. If you are stuck, do ask me, please leave a comment, like and subscribe. It's very, very appreciated when you do that. Take care of yourselves, and please do tune in for the next video. So I hope to see you again all soon, and goodbye from me for now. Take care.